For today, we're gonna continue our lecture about failure. Give me a second so I can close my door first. About a fracture, yeah, patah. Okay, and before we continue, we can maybe we can watch one video about a fracture, which is from uh, the video that I have put it here. Yeah, let me check this one. Okay, so let's watch video. Some example about fracture.
Welcome back once again to the teaching laboratories here in Camper Hall on the UC Davis campus. In this segment, we're going to talk about fracture toughness, a concept that indicates how important it is to be aware of small defects in the material. Defects on a microscopic and even millimeter scale that can lead to catastrophic fracture. In introducing fracture toughness to our discussion of important things that we should know about material science, we've really added a fifth very important parameter on top of those big four that we got from the stress strain curve. In this case, fracture toughness gives us a way to quantitatively determine when a flaw size is critical. And as I said at the opening, these are flaws that can be fairly substantial in size. A few millimeters deep crack on the surface of a material. Well, we probably can think of no more iconic example of a defective material than the Liberty Bell, which for the lifetime of the United States has represented liberty, but is also has a very famous and large crack that is visible on the surface. And in fact, that crack is one that was a concern when the Liberty Bell was moved in 1976 on the occasion of the bicentennial of the American Republic. And in order to make the Liberty Bell more accessible to a large number of potential tourists in Philadelphia, it had to be moved to a new location. And in moving, there was substantial concern that that crack could be a critical one, and by the concept of fracture toughness, could have completely destroyed this great iconic American image. And so as a result, sophisticated acoustical equipment was used to monitor any potential growth of that crack, and fortunately, no such crack growth did occur. So from something as famous as the Liberty Bell to something as routine as everyday structural components and engineering designs, we have to be very sensitive to the possibility of the motion of such cracks, how they might begin and how they might grow until they become what we call a critical flaw size. So now let's look at exactly what these terms mean and exactly what defines a critical flaw that can lead to catastrophic failure.
Okay, so that's it about fracture toughness. Yeah, the famous example in the United States at that time. You can see the bell, the Liberty Bell. They have substantial crack, retakan. Okay, but why the bell doesn't, if the crack doesn't grow and then it just become broke, it's because there are some things that need to be done. Okay, so let's go back to here. Okay, so I'm sorry, PPT still in Indonesian, but I think still I can still explain it. So the ability of a material to prevent a fracture even it has a crack is called fracture toughness. Okay, so where is it? Okay, this one. Ukuran ketahanan bahan terhadap patah rapuh ketika ada retakan. So fracture toughness means, again, we know already that the resistance of a material when you have for a fracture if you have already the crack. Okay, so in here we know that the fracture toughness Kc is actually a constant multiplied with the critical one and then a square root of Va. Yeah, we have talked about that one last week. And then we usually use the KIC or K1C, which is the motion of the crack. Yeah, the motion of the crack. So if you have a crack over here and then you have a tensile load that way and this way, like perpendicular to the crack direction, it is called KIC. Okay, and it is defined as a constant multiply with the stress and also square root of V multiplied with A. Okay, and then last week we also learned about this is the material, and then you can see this is the sigma Y or the yield stress, yield strength, kuat luluh. Okay, when it starts to change from elastic deformation to plastic deformation, and this is actually the KIC. Okay, for metal, the KIC is relatively high. Okay, so like this one is from aluminum alloys, titanium alloys, steel, a tempered steel or another tempered steel. It is quite high. Okay, so if the fracture toughness is high, so that means even though in the material there are some crack, okay, the material still will able to withstand the load without the crack will propagate and also will make a broken or make a failure. Okay, however, if you look at here this one beton, yeah, or concrete, or this soda lime glass is glass, yeah, the window glass, or aluminum oxide, it is a very small fracture toughness. Okay, so that means when it has some crack, it won't be able to withstand those crack, and then the crack will easily propagate, will easily grow, and then it will cause the failure. Okay, and this is for polymer. This is polystyrene. If you know styrofoam, yeah, that is polystyrene. This one is PMMA. PMMA is the acrylic. The acrylic that you see in it's like glass, but it's not a glass. It's a acrylic, yeah, acrylic polymethyl methacrylate. This one, this is KIC, and this is a polycarbonate, the one that we use for fiberglass or the roof of the house, something. Okay, so here you can also see the typical properties of this metal. So the metal has a quite high yield strength, and then quite high toughness as well. And then here for polymers, quite relative low yield strength and also relative low KIC as well. Okay, so here then when we design something, when we design for example, how is the maximum stress that we need to apply for a building, okay, or for inside a tank or inside a reactor. So we have to check it, how much the flow that it has already there. Okay, so if you have A, which is A is the length of the crack, okay, the length of the crack there. Okay, if you have A, which is the length of the crack, Or and then you know the KIC, because KIC is actually unique for every material, so you can see the map, or you can see the book, the handbook, to get the KIC of your material. You need to check the critical stress. Okay, so the critical stress would be the KIC divided by the y square root of v multiplied with a. Okay, so then this gonna be your critical stress, tegangan kritik. Okay, so that means if you apply the stress, which is if you apply stress that's higher than the critical strength or the critical stress, then it probably that your crack, the crack there one will propagates, akan menjalar, propagates, and later on will cause a failure. Okay, so the next one, if you have a KIC and then you have already know what is the limit of your stress, then you can check what is the maximum size of flow or maximum size of crack that it still you able be withstand without so the material can still perform okay, all right, without any fracture. Okay, so this is all some NDT or non-destructive testing. I explained to you before. We can use a scanning electron microscope, but we have to cut the specimen and then put in the laboratory. We can use a dye penetrant, we can use ultrasonic optical microscope, and so on, or acoustic emission and radiography to check the defect location. And okay, and after that, in the plant, we can we can do some mapping to check about our equipment, which one is still okay, which one has a quite critical size of flow, and then which one this equipment that need to be repaired, okay, with maybe welding or with some other treatment. Okay, so here, for example, we have a spherical tank, or maybe I can explain with the wait, okay, maybe I can explain from the book. Yeah, this one, Callister. So let me just explain it with the okay. So for example, let's see that this is one example. Okay, so let's see, we want to check material specification of a pressurized spherical tank. Okay, so do you know about spherical tank? Tangki bola, yeah. Spherical tank, usually we need that to store a gas. Okay, so we consider a thin-walled spherical tank with the radius of r and the thickness t. Okay, it can be used as a pressure vessel, and then we need to we have to design, and then so first one we have one design. The first one, the design is leak before fracture. Okay, so the one design actually we want to have a formation of critical size. Okay, so the first one is okay, sorry. So the first one, so one design is called yielding of the wall. So if the wall can start yielding before it break. Okay, so if the wall start yielding, mulai kuat luluh, ya, it start plastic deformation, and then we want to know which critical size that we need to know that one before rapid propagation. Okay, so if we can observe a plastic deformation on the wall, and then we can maybe stop the tank, and then the pressure can be released before the occurrence of catastrophic failure. Okay, so material should have a large critical length. Okay, and then on the second one, it may be alternative design is actually called leak before break. So what if the pressure or the tank has a crack, which is the crack is in the length of the thickness? Okay, so it can leak first, so the gas can leak first without it's broken, and then when the gas leak, and then maybe it can be smelled or it can be detected with some indicator. Then after that we can okay, we know that there's gas leaking, and then we can stop the operation and then check that one. Okay, so here first for the first criteria, and we have also need to know that in Pelautan process, yeah, in the Pelautan process or in ASME code, American Society of Mechanical Engineers, there are some formula about how to calculate what is the correlation between the stress and also the pressure and the thickness in a spherical tank. Okay, so here, so for a spherical pressure tank, the stress is actually the function of pressure, P, and then multiply with the radius, divide by 2, and also divided by the thickness. Okay, so here, so the first criteria, we want the wall stress should be less than the yield strength. Okay, because we don't want the stress should be more than the yield strength, because if the stress is more than the yield strength, then the material will undergo plastic deformation. Okay, and we want to avoid that. Okay, so here using the equation is actually, and we can also add a factor of safety or safety factor N. Okay, so from the formula, if you consider that KIC, the fracture toughness, is actually equal to Y, and multiply with the stress that is applied. Okay, and the stress that is applied is actually the yield strength, strength, and divided by the safety factor. Okay, the safety factor can start from 1 unto 4, yeah, sometimes can be 2 or something. This to ensure that we have a factor of safety. And then square root of alpha sigma, the phi multiplied with AC. Okay, so where A is the critical length. So when we try to rearrange the equation, and then we solve the AC, so we can calculate the critical length of the tank, yeah, the critical crack of in the thickness of the wall by calculating this one. Okay, so therefore the critical crack length is proportional to the square root of KIC and so the square of KIC and sigma Y, like this, where's the basis of the ranking of metal alloy in table B4. So let's look at the table B4 here. Okay, there, and then you can see that so which one that it's about in B5, yeah, B5. I think it should be B3, yeah, this one. Critical length. Okay, so square root of KIC divided by Y, yeah, square there. Okay, so you can see here that this is the rank of the metal alloys that you can have with the value. So I think so you can, and then later on you can match them with the unit cost, maybe, if you consider about the finance and also the economic scale of that one. So you can see that this is the medium carbon steel 10400, has a very high, almost 2 times of the magnesium alloys, or almost 3 times of the aluminum alloys. Okay, so that's why for the tank, for the material for the tank, medium carbon steel is actually a really good idea. Okay, because they have a good KIC over sigma Y square, which is it can so if you have a crack, it can withstand the crack propagation. Okay, the second one, And the second one, how about if we have leak before break? Okay, so leak before break, that means when you have A equal to the thickness. When you have the A, which is the half internal crack, is equal to the thickness of the wall. Okay, if you substitute the A and into T into here the equation, it will give equation 8.5. Equation 5, it will give K1C KIC equal to the Y multiply with the stress multiply with this sigma and T. So if you put the T into A, and later on from here because the thickness is function of the pressure and radius and also the stress, and then you can substitute that into a pressure. So even given a spherical vessel with some radius of r, the allowable pressure would be proportional with KIC and divided by sigma y here. Okay, so here we also get we can rank several material here, yeah, and then if you look at here, then again the medium carbon steel can have is a good KIC square divided by sigma y. Okay, so this actually tells us about the material selection case where for the thin wall spherical vessel, which material that we need, we can look at what is the design that we would like to see. Is it before plastic deformation, or is it leak before break criterion like this? Yeah, is it using yielding criterion or using leak before break criterion? And then you can choose which material. Yeah, unfortunately, fortunately, here you have medium carbon steel, and then both of the medium carbon steel is also the cheapest of all. Okay, so it is quite cheapest compared to the others, compared to titanium, compared to aluminum, and so on. So if the gas that we have is actually just natural gas or hydrocarbon gas, and there is no corrosion gas, it's not specialized gas, then you can use just the medium carbon. Okay, so that is one of how we select the material. Okay, so that is about a fracture. Okay, the next one, let's look at the wait, I'm still I think I'm still screen sharing something, so let me close that one, and let's go back to the okay, so this one. Okay, and this one also there's some example, so you can try to check it by yourself. So here's actually the plane wings, yeah, sayap pesawat terbang. So it is based from the aluminum alloys, and you have the plane strain fracture toughness, or the KIC 26 megapascal square root meter, and then you have the stress actually has the internal maximum of 8.6 millimeters. Okay, so you have to calculate the stress, tegangan penyebab patah, if you have internal crack around 9.0 millimeters. So this one I have given some clue, yeah, so you can just try it by yourself and just do calculation, and then you should be able to do that. Okay, so now let's continue with the next one is about fatigue. Okay, so fatigue is actually a type of failure. It's actually on the structure, and it actually have the dynamic loading and dynamic stress, and it actually fluctuates. Okay, for example, on a bridge, bicycle, okay, or airplanes, or machine components, and so on. Okay, and fatigue is actually almost 90% of metal failure, because it doesn't have the initial crack, or there is there's nothing, yeah, tanpa gejala awal. Okay, there's no indication first, but after that it's gonna fatigue. Okay, so it is close to the morphology of the fatigue, close to brittle fracture, patah rapuh. Okay, because it's just gonna start cracking like that. Okay, so before I explain to you in a video, let's check this one here. So this one, so we actually idealize about the fatigue. So if it start from 0, it has a maximum load, and then start going back again, and then it's going to the minimum load. Okay, so it's like a tensile, and then stop, and then pressure load. Okay, and then compressive load, and then go back again, and then tensile load, and then go back to the initial one, and then compressive load, and so on. And then it may happen for like 100 and 1,000, and can be 1,000 cycles. Okay, so here it's actually, so we have a repeated stress cycles, looks like in a wave, yeah, gelombang. Okay, so the maximum one is called sigma A, and the maximum is actually the M is actually the sigma maximum, and the minimum divided by 2. Okay, when also sigma R is defined as the maximum of minus the minimum one, and this one, the ratio is actually sigma minimum divided by sigma maximum, and sigma A is actually the sigma R divided by A. Okay, that one there. Okay, so here, so we also have a SN curve, but before we saw SN curve, so let's watch a video about fatigue and how to check it, and then after that we can see the questions about, we can see some calculation about fatigue. Okay, so let's share some screen over here. Okay, it should be in fatigue. You can watch another one as well, yeah, from the Professor Shackelford, but it's all about all the fatigue definition and so on. So you can watch. It's quite long. So I'm actually now would like to explain to you about this one about fatigue test. So let's have a look about 12 minutes video.
Fatigue test. Many everyday items are not loaded uniformly, but rather non-uniformly with periodically changing loads. This is quite obvious in off-road biking. Frames, handlebars and wheels are subjected to high alternating mechanical loads. It is just as obvious in the case of a garage door spring. The spring is unloaded when opening the door and loaded when closing the door. The connection rods of this old compressor have endured a large number of rapidly changing tensile and compressive forces. Even when cycling quite moderately in the city, many components are exposed to periodically varying loads without us being aware of it. The crank arms are alternately under load, then swing back almost load-free, are under load again with the rhythm of pedaling. The spokes, the pedals, even the individual links in the chain are stressed periodically. Also, the railway bridge over the River Rhine, seemingly totally addressed, alternately has to bear the additional burden of a heavy freight train and then only its own mass. Aircraft experience quite different stresses during takeoff and in turbulence than on ground. This type of loading is generally termed fatigue loading, and the material responds to it, fatigue. The term fatigue is used because it takes some time for the failure to occur under repeated loads. The problem with materials is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had borne the opening and closing of the garage door about 60,000 times before it finally fractured. The broken exercise equipment, a torn blade of a fan, a bandsaw blade full of cracks, the broken screw, a defective universal joint, and many other examples show how important this phenomenon is. Each day, thousands of items break due to cyclic, often repeated loading. How can we make sure that all these components withstand the cyclic loads? To achieve this, one has to test the materials appropriately. We intend to measure the fatigue strength of a frequently used steel in our laboratory. Hot-rolled steel rods made from the structural steel S235JR are used as base material. In order to eliminate the influence of the surface and to stress the material in a well-defined manner, suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 millimeters. The material tester goes to the workshop to get 10 specimens manufactured from the rods, not just one. All of the specimens are as identical as possible. Back in the lab, he has all specimens ready for use and picks out the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with 2 half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The specimen is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted, and there in turn, a mass. An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest, and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces. At first glance, the fracture surface looks unimpressive. A closer look reveals 2 regions: the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks, starting at the surface of the specimen. What does the fatigue crack propagation area look like at higher magnification? One of the fragments is carefully placed on the specimen stage of our scanning electron microscope. Now we can investigate the fatigue crack propagation area in detail. In some places, but not everywhere, parallel grooves and ridges can be seen, the so-called fatigue striations. Each groove and each ridge has been formed by an individual load cycle, a typical phenomenon. Of course, now we want to know how many load cycles this material can endure with other loads. For this purpose, the material tester picks the next specimen from his supply and installs it into the fatigue testing machine. He chooses a higher alternating load for the second specimen. a tensile force of 7.5 kilonewtons, and a compressive force of 7.5 kilonewtons. Under the increased load, the specimen is only able to withstand 43,600 cycles to failure. The third specimen is only tested with a cyclic load of 6.5 kilonewtons. Under this reduced load, it does not break even after 3 million load cycles. Additional specimens complete the series of measurements. Some of the specimens are tested with the same load we've already used. In this way, we get an impression of the range of scattering. To compare materials in a fair way, the different cyclic loads are converted to the respective stresses acting in the specimen. In this case, the stress alternates sinusoidally around the mean value, which is termed mean stress sigma m. In this series of tests, the mean stress is 0. The stress amplitude is labeled with the symbol sigma a. For graphical representation, the SN diagram is used, also termed Wöhler diagram. In an unusual manner, the predetermined variable is plotted upwards on the y-axis. It is the stress amplitude sigma a. And the result of the test, the number of cycles to failure n, is plotted to the right on the x-axis. To fit small and large numbers into the diagram, the x-axis is not scaled linearly, but logarithmically. The first specimen was loaded with 7 kilonewtons. This corresponds to a stress amplitude of 248 newtons per square millimeter. Under this stress amplitude, it broke after 381,000 load cycles. The second specimen was loaded with 7.5 kilonewtons. This corresponds to a stress amplitude of 265 newtons per square millimeter. Under this stress amplitude, it broke after 43,600 load cycles. And these are the results of the other specimens which have been tested by us. When additional specimens are tested and the results are displayed as a curve, it becomes clear that this material will not break below a certain level of stress amplitude, even after a very large number of cycles. This stress level is termed fatigue limit sigma capital A. For most steels with body-centered cubic structure, the fatigue limit is reached after 10 million load cycles at the latest. It must be noted that the experimental results scatter considerably. Therefore, instead of a sharp curve, a statistically defined scatter band is commonly used. Of course, most users don't load their components with a constant cyclic load, but rather in an irregular manner. Therefore, these components have to be tested under this type of loading, termed operational loading. In this test rig, critical bicycle components are loaded similarly to practical use. Stem and handlebar must endure the typical bending and torsional loads for a sufficient number of cycles. Only then they are approved for serial production. Moreover, the fatigue strength does not only depend on the material. The mean stress has an important influence, the shape, the surface quality, environmental conditions, and much more. Not an easy story. Before an aircraft is allowed to take off for the first time, it has to go through extensive stress tests. The wings and many other elements are cyclically loaded in large test rigs. This later ensures the safe operation of the aircraft. Nevertheless, particularly important components are repeatedly examined for fatigue cracks in the course of operation. The tram, for instance, has to go into the test hall at regular intervals. Experienced staff use ultrasound to examine special components, especially the wheel set axles, to check whether they are still in perfect condition. Aircraft are also inspected for fatigue cracks at reasonable intervals. This helps us to depart for air travel without worry and land again safely.
Belum aja dulu ya. Oke, ya. Okay. Alright, so that is about the fatigue test. Okay, so let me just explain. Okay, just let me go share screen again. Where is it? Okay, so like in the video for the fatigue test, okay, we have the graph, which is stress amplitude. Yeah, so here you can see that each point is actually one's typical stress amplitude, and then you can see when is the cycles of failure. Okay, and then there are two types of metals. The first one is the metals that have a fatigue limit, okay, usually for BCC, but for the second one is the FCC metals that doesn't have fatigue limit. So there are, the first one looks like this. Okay, this is usually for iron, the BCC structure, and then here is for aluminum or copper or non-ferrous. They doesn't have fatigue limit, tidak punya batas lelah. Okay, so here you can imagine. So for example, if you expect that your equipment is for maybe, let's say, up to 10 to the 8 of cycles, okay, so then you have to check what is your fatigue strength, okay, or what is your stress amplitude. And once you know your stress amplitude, then you can go back. So this is the stress amplitude, or the sigma A. So you can check, so what is the maximum of sigma maximum and the sigma minimum that it can be applied for your loading. Okay, but if not, then or the second one, if you also know about the sigma maximum and the minimum, you can check how much it cycles to failure. So if we can predict that, or we can so if we can start to predict that, we can check what is the maximum cycles of failure, so we can start to change the material before it starts to failure. Okay, because before catastrophic failure. Okay, so here this is the cycle of failure for some maximum stress for S, yeah, the maximum stress S of this one, yeah, the maximum stress S, that's the one, for some cycles. Okay, here we have seen that there's titanium alloys, there's magnesium alloys, or aluminum alloys, and cast iron, and so on. Okay, so here's gonna be the origin, and this is the direction of rotation. It's gonna be the final rupture. Okay, so the process for the failure, for the fatigue, again, if you want to know about fructography, kegagalan, ya, or the ilmu tentang patah, ya, like that, the fructography, you can see where is the slow propagation, and then because of the fatigue, and after that there's a very brittle brittle fracture, kegagalan cepat because of those brittle fracture. Okay, and and then here we also see that if we apply some stress amplitude, if we apply a higher stress amplitude, for example this one, the cycle to failure will also less than that one. Okay, so for example we have the green one. The green one has stress amplitude of higher than the blue one, and also the red one here. If you look at one certain stress amplitude, there you have very low cycle to failure compared to the maximum one. Okay, and then also to reduce the fatigue limit, or to increase the fatigue limit, or to increase the fatigue limit, and to reduce the fatigue, we can also change the design. Rather than a very sharp edge like this, we have make a fillet like this, lebih rounded. Okay, so then the concentration of the stress concentration will be distributed. Okay, and this also, for example, this one from the stress amplitude between the normal and the short pin like this, it is will quite actually will increase the residual compressive stress. Okay, so this is some example. You can have a look as well for your practice. And the last one is for creep. Okay, the creep is actually the permanent deformation because of the higher high temperature and also a static load. Okay, if you have a static load and also you have a high temperature, then you will have a creep atau mulur. Okay, so here creep, because it's mulur, yeah, the creeping. So the indicator that we're looking at is actually the strain. So the creep strain is actually will increase with the time until it starts to rupture. Okay, next example, creeping, for example, if you have a raincoat, jas hujan, and then you put it in the hook, and then you just wait for a long time, it's gonna be creeping, or which is it won't apa ya, akan mulur, ya, like that one. Okay, so here we have the primary area, and then the secondary area, and then the tertiary area. The first one is transient, and then this one is a steady state. We start strain hardening, and this would be acceleration of the creep because of the increasing of the creep rate. Okay, and then the creep rate also we can see it again in the mapping. Usually it is at temperature lower than 0.4 of the melting point. So let's say if you have a metal, and then you operate the reactor around maybe 500 degrees Celsius or 400 degrees Celsius. Let's say you have a reactor for gasification or something like that, yeah. And then so you have the metal, and you operate at quite high temperature, but still below the melting temperature, and then you have a static load, then you will have a creep. Okay, so here so the temperature should be lower than 0.4 of the melting point, and you can see that the strain is going to increase at higher temperature compared to the low temperature. If you have higher temperature, if you have higher stress, ya, Anda punya beban yang tinggi atau Anda punya temperatur yang tinggi, that will cause a mulur or a creep strain for that one. Okay, here one also we can see that the maximum stress, we can actually measure the maximum stress compared with the rupture lifetime. Okay, with hours. So it's actually quite increasing as well over here. So there are the rupture and also the steady state creep. Okay, so that's why for the alloys for high temperature, paduan pada suhu tinggi, we have to have more customized metal for high temperature. For example, we can use superalloys made from copper, nickel, and chrome, something like that, but it's very expensive. Or if you want to burn something, we use refractory metal, or just use refractory bricks, yeah, for that one. Okay, and then cobalt, nickel superalloys, and then there would be some of the example for the high temperature. Okay, so that's it. There are three types of failure. The first one is fracture, patah. The second one is fatigue, patah lelah. And then the third one is creep and or mulur. And then for the last one, let's watch one more video again about the creep. Again, it is from the book, yeah. Let me again stop share. Maybe I can go back here. to the crib video. So if you're interested with some of the calculation, I also put some explanation similar with I'm explaining from the Professor Shackelford, so you can have a look as well here. And then let's watch about 2-minute video about crib deformation, about the the introduction about crib deformation, so we can know what is the application with crib deformation.
We're here in the central heating and cooling plant at UC Davis, near the student dormitories, where we provide, among other things, the hot water for those dorms. So it's an introduction to the concept of creep deformation, which is defined simply as materials being used at high temperature, under high pressures for long periods of time. And so when we look at materials under creep deformation, we'll look at the various categories of materials. We're reminded of those various menu of materials introduced in our first segment. And of course, we focused at that time on metals, ceramics, and plastics or polymers. Whereas we'll primarily talk about metals and ceramics today, we shouldn't lose sight of the fact that polymers, which were our example of covalent bonding, very strong bonding between adjacent carbon atoms in a polymeric chain molecule, can actually be relatively weak and easily deformed because of weak or secondary bonding between adjacent molecules. So those noodle-like molecules that can easily slide past each other under modest stresses can also be subject to creep deformation at relatively low temperatures. Even at room temperature, they can exhibit these polymeric materials, that kind of extensive plastic deformation under significant loads over long periods of time.
Okay, so that is about a creep deformation, where you have, if you have a high pressure, a high temperature, and also under distress. Okay, so everyone, so for now the our chapter about failure is up. So about fracture, fatigue, and also creep. Tomorrow we will continue our lecture again, 2 hours lecture about phase diagram. So I hope you can prepare them by I'll upload the module just after this, so you can check. If you think you can print it out, it's good if you can print it out the phase diagram. If you're using tablets, you can maybe check your tablet, and then you can read it from your tablet. So actually tomorrow we're gonna start learning about phase diagram, and also read about how to read a phase diagram. Okay, everyone, so thank you very much for your attention. So I'm gonna see you again tomorrow. Bye bye.
Thank you very much.
Okay.